Hello and welcome. I'm so glad to be with you again as we continue to build our understanding of core statistical concepts in educational research. Today, we're going to focus on ideas that will help us interpret data in meaningful ways, particularly in the context of student achievement, learning environments, and educational equity. We will not focus on memorizing any one formula or solving a particular problem. Instead, our goal is to understand how to think about data in terms of variability, relationships between variables, and patterns that can emerge in educational settings. Let's begin with a concept that lies at the heart of so many educational statistics, the normal distribution. Imagine for a moment you are a school psychologist examining reading scores of third graders across a district. You have collected the data from all students who took the district-wide reading assessment. When you graph the scores, you notice something beautiful. The majority of students score in the middle range, while fewer score very low or very high. This is the classic bell-shaped curve, the normal distribution. A normal distribution is a symmetrical, unimodal curve. That means it has one peak, and the values taper off evenly on both sides. In educational settings, we often assume things like test scores, IQ scores, or even attendance rates are normally distributed. Although this is not always true, and part of our job is to test that assumption. When you see a histogram or frequency polygon that shows that beautiful symmetry, it suggests a well-behaved data set, but we always need to be cautious about assuming it without evidence. Now let's talk about two important properties of any distribution, the mean and the standard deviation. The mean is the average, what most people think of as the middle score. But the standard deviation tells us how spread out the scores are around that mean. In a tight distribution, most scores are clustered close to the mean, while in a wide distribution, scores are more spread out. Let's bring this to life with an example. Suppose at a local high school, the average ACT score is 22 and the standard deviation is 2. If most students score between 20 and 24, that's one standard deviation above and below the mean. Statistically, in a normal distribution, about 68% of all scores fall within one standard deviation of the mean. That's why these boundaries, mean plus or minus standard deviation, matter so much. Sometimes we want to compare individual student scores to the overall group. That's where the z-score comes in. A z-score tells you how many standard deviations a particular score is from the mean. For example, if a student scored 24 on that ACT and the mean is 22 with a standard deviation of 2, we'd calculate the z-score by taking the student's score, subtracting the mean, and dividing by the standard deviation. That gives us a z-score of plus 1. This tells us that the student scored one standard deviation above the mean. Z-scores also help us understand percentiles. Imagine you're advising a student who scored in the 84th percentile on a standardized reading test. That corresponds roughly to a z-score of plus 1. It means that student performed better than 84% of the test takers. In P to 12 education, this information helps guide instruction, identify students for enrichment, or flag those who may need extra support. Sometimes distributions are not normal. Let's talk about skewed distributions. Not all data sets are symmetrical. For example, if we look at reading fluency scores in a kindergarten classroom at the beginning of the school year, we might see that most students are just starting to decode words, while a few come in already reading simple sentences. The scores pile up at the lower end with a fewer higher outliers. This is a distribution that is skewed to the right, also called positively skewed. Conversely, if nearly everyone does well on a simple review quiz, but a few students do poorly, we end up with a left skewed or negatively skewed distribution. In these situations, the mean gets pulled in the direction of the tail. That's why in highly skewed data, the median might be a more representative measure of central tendency. We also encounter distributions that are bimodal, meaning they have two peaks. One real-life example might be in a college's writing placement exam scores, where you have one group of students who took AP English and another group who did not take advanced coursework. These two groups may cluster around different average scores, leading to two peaks in the data. Another important idea that helps interpret test results is the concept of floor and ceiling effects. A floor effect occurs when many students score at the lower end of a scale, not because they lack ability, but because the test is not sensitive enough to capture their differences. This might happen if a test is too hard for the group. Conversely, a ceiling effect occurs when most students score at the top, making it difficult to distinguish high performance. This could happen in an honors class where the material is too easy. Both effects limit the usefulness of our data and can obscure real variability among learners. Now let's consider the concept of standard error. This is a measure that tells us how much variability we can expect in sample means if we were to repeatedly take samples from the same population. For example, suppose a researcher at a state education department wants to estimate the average math score of eighth graders across the state. They select a random sample of 200 students. The mean of that sample gives them a point estimate, but it's unlikely to be perfect. That's where the standard error comes in. It helps quantify the uncertainty around that estimate. And when we combine a sample mean with a standard error, we can construct a confidence interval. A 95% confidence interval means that if we took 100 different samples, about 95 of them would contain the true population mean. In educational research, we often use confidence intervals when reporting results from surveys, test scores, and evaluations. It helps policymakers and educators know how precise the results are and how much wiggle room there is before drawing conclusions. Let's say you're evaluating a summer literacy program for third graders. You find that the average reading score increased by 5 points with a 95% confidence interval of 2 to 8. That interval suggests the true improvement is somewhere between 2 and 8 points. And we can be fairly confident that the program had a positive effect. But if the confidence interval includes 0, like -1 to 5, we cannot be sure that there was a real gain. Let's now turn to correlation, which is a measure of the relationship between two variables. The correlation coefficient, denoted as R, ranges from -1 to +1. A positive correlation means that as one variable increases, so does the other. For example, in early elementary classrooms, we often see a positive correlation between the number of books a child has at home and their reading level. More books tend to go hand in hand with stronger literacy outcomes. A negative correlation means that as one variable increases, the other decreases. In higher education, we might find a negative correlation between the number of hours students work off campus and their GPA. The more hours they work, the more their academic performance may suffer. Not necessarily because of causation, but because time and energy are finite. It's essential to remember that correlation does not imply causation. Just because two variables move together doesn't mean one causes the other. A third variable could be at play. For instance, let's say we find a correlation between screen time and behavior issues in middle school students. That does not prove that screen time causes behavior problems. Perhaps students who already struggle behaviorally are more likely to spend time alone on screens. Even weak correlations can be meaningful. In educational research, a correlation of zero point 0.3 might be considered small statistically, but it could represent an intervention that helps struggling students catch up, an effect that is practically important, even if modest. One way to visualize relationships between variables is through a scatter plot. This graph plots two variables on the x and y axis, allowing us to see patterns, trends, and outliers. For instance, you might chart school attendance on the x axis and final grades on the y axis. A clear upward trend would suggest that students who attend more tend to perform better. Let's consider a few real life research scenarios to bring this all together. First, a district is implementing a new culturally responsive teaching program. Researchers collect student engagement scores before and after implementation. They graph the data and find the distribution has shifted. Engagement scores are no longer skewed, but are more normally distributed, indicating more students are reporting moderate to high engagement. That's a powerful pattern. Or think about a graduate program evaluating a writing seminar aimed at first generation college students. Pre and post intervention scores on academic writing assessments are compared. A scatter plot of participation rates and score gains reveals a modest positive correlation, suggesting that students who attended more sessions tended to improve more in writing. Or imagine a teacher researcher in a fourth grade classroom interested in self regulation. She gives her students a self regulation scale and compares scores to reading comprehension levels. She finds a correlation of 0.45, a moderate relationship. This helps her justify integrating more social emotional learning into her literacy block. Lastly, consider the ethics of interpreting data. In educational settings, numbers often carry real consequences, whether for identifying learning disabilities, placing students in gifted programs, or evaluating teacher effectiveness. It's our responsibility to ensure that data interpretation is honest, contextual, and culturally aware. No statistical output should be separated from the lived realities of students and teachers. So, as you prepare to analyze data, whether for an assignment, a research project, or a real world educational initiative, I encourage you to think beyond formulas. Ask, what story is the data telling me? Are there patterns that deserve more attention? Are there relationships that suggest a deeper dynamic worth exploring? Statistics, at its best, is not just about numbers, it's about uncovering insight, understanding variation, and driving better decisions for students and communities. Thank you, and I look forward to seeing how you apply these concepts in your own research and practice.